This problem is a modified version of a free response question from a former AP Physics exam. Here, mass m slides down a frictionless ramp and has a speed of 3.5 v0 when it collides with the 1.5 mass block, which is at rest at the bottom of the ramp. After the collision, the 1.5 m block moves to the right with a speed of 2 v0. Because there's a collision that's taking place here, I would really like to define what I mean when I say before the collision and after the collision. The mass m starts at the top of the ramp, but the collision doesn't take place until after the box comes all the way down to the bottom of the ramp. And so when I talk about before the collision, what I'm really talking about is this moment when the block is at the bottom of the ramp and it has a speed of 3.5 v0, but it hasn't collided quite yet with the 1.5 m block. So I'm going to draw a little picture here, which is before the collision. Before the collision, we have the block with mass m, which is moving to the right with a speed of 3.5 v0, and the block with mass 1.5 m, has no speed, v equals 0. And so that's what the picture looks like before the collision. And then after the collision, we're given some information. It says that the 1.5 m block moves to the right with the speed of 2 v0. So after the collision, we have the 1.5 m mass, which is moving to the right with a speed of 2 v0. And what I'd like to figure out is, after this collision has taken place, what is that final speed? I'm going to call it just v. What is the final speed of that block with mass m? Okay, so this is the thing that I'm trying to figure out. In order to do this, I need to compare the momentum before the collision to the momentum after the collision. If momentum is conserved, then the momentum before the collision, which I'm going to call pi, is equal to the momentum after the collision, which I'm going to call pf. The initial and final momentum should be equal to one another, so long as there are no external forces that are acting on these blocks. Momentum, in general, which is a vector, is equal to mass times velocity. And so before the collision, I need to decide how much momentum is there, which boxes are moving, which boxes have momentum. And so the way that I do that is I will write m times v for everything that's moving, and I will plug in what its mass is and I will plug in what its velocity is. Initially, okay, which is right before the collision happens, the block with mass m is moving with a speed of 3.5 v0. So that block has some momentum. Its mass is capital letter M, and its speed is 3.5 v0. That is the only initial momentum. If you wanted to also include the momentum term for the second block, which isn't moving, we could just write plus 0. Since the velocity of the 1.5 mass block is 0, its momentum will be 0 initially, before the collision. After the collision has taken place, the final momentum is going to be the momentum of the 1.5 m box for sure, because it has a velocity. So its mass is 1.5 m, and its velocity is 2 v0. And then the momentum of the box with mass m, which is its mass m times some speed v. I don't know what that speed v is. I've been very careful here about indicating the directions of the velocities. All of these velocities are positive, they point to the right, and so I should get an answer for v which is sensitive to that sign convention. So now I want to neaten up this equation a little bit. On the left hand side, I'm going to have 3.5 m v0, and on the right hand side I'm going to have 1.5 times 2, which is 3 m v0, plus m times v. If I subtract this term, 3m v naught, to the other side, I'll have 3.5 m v naught minus 3 m v naught, which is just 0.5 m v naught equals the term on the right, m times v. And so initially, the entire thing that I was trying to do here was solve for the velocity of this block with mass m after the collision. And so the last thing I need to do is recognize that the mass on both sides cancels. And so the velocity of that block after the collision is 0.5 times v naught, which was a constant that was given as, some multiple of the velocity that the block has when it gets to the bottom of the ramp. And so this is my answer to the first part of this problem. The next thing that I would like to do is I would like to determine whether this collision is elastic or inelastic. These are the two primary types of collisions that we're going to be talking about, and we need to have a way of determining whether a collision is elastic or inelastic. The primary difference between elastic and inelastic collisions is whether or not energy is conserved. In both of these types of collisions, momentum is conserved, so Pi equals Pf in both types of collisions. So I could write momentum conserved for an elastic collision, momentum conserved for an inelastic collision. But in an elastic collision, energy is also conserved. But in an inelastic collision, energy is not conserved. And so we need to do an energy analysis to figure out, is the energy at the beginning before the collision equal to the energy after the collision? And if they're equal, then the collision is elastic, and if they're not equal, then the collision is inelastic. After all of the gravitational potential energy of the block with mass m is converted into kinetic energy, and that block is at the bottom of the ramp, the only energy that's present in the system is kinetic energy. And so if the kinetic energy before the collision is equal to the kinetic energy after the collision, then the change in kinetic energy before and after the collision would be equal to 0. And so what I'm going to do is figure out what is the change in kinetic energy. What is K final minus K initial? If the change in kinetic energy is 0, then the collision is elastic, energy is conserved. And if the change in kinetic energy is not 0, then energy must not have been conserved in the collision, and therefore it would be inelastic. So first I need to find what is the final kinetic energy of the system. The final kinetic energy is due to both blocks. And the reason for that is because both blocks have some kinetic energy. So I have to add up the kinetic energies of both. The kinetic energy of the first block is 1/2 times its mass m times its speed v, which we found in the first part, which was 0.5 times v naught squared, plus the kinetic energy due to the other box, which is 1/2 times its mass, which is 1.5 m, times its velocity, which is, after the collision, 2 v naught. So this entire term here is the final kinetic energy. The initial kinetic energy isn't as complicated because right before the collision, only one of these boxes is moving, and so only one of the boxes has kinetic energy. So K final minus K initial, and K initial is 1/2 the mass of the box with mass m times its velocity, which was 3.5 v naught, and that is squared. I would strongly suggest to you from here to go through and try to multiply some of these numbers through, square the speeds, pull the coefficients out in front, and add all these terms up together to see what you would get. What you should find is that the change in kinetic energy ends up being equal to minus 3m v naught squared. And so the fact that the change in kinetic energy is negative means that some of the kinetic energy must have been lost in the collision. The kinetic energy before the collision and after the collision are not equal, and therefore cause the change in kinetic energy to be not equal to 0. So from here, I could say that ultimately the collision is inelastic. I used the fact that the energy was not conserved to determine that the collision was inelastic. Here, after the collision, the two boxes are moving with two different speeds, 2 v0 and 0.5 v0. Those are the two different speeds of the blocks after the collision. And since they have different speeds, they must not be stuck together. So just because a collision is inelastic doesn't mean that the objects stick together. Inelastic collisions are defined by the fact that energy is not conserved. It just so happens that sometimes the objects stick together, sometimes they don't. When the two objects do stick together, energy is not conserved, and it turns out that when they stick together, they lose the maximum amount of energy. The most energy is lost when they stick together. So here, even though they don't stick together, energy was lost, which means it's still an inelastic collision.